Good morning, students. In last class already about torque on magnetic dipole and related problems were completed. Today we are ready to discussing about what is a solenoid and when current is flowing through a solenoid, how it is behaves. Those concepts we are ready to discussing here, students. So first of all, we want to discuss about solenoid. Solenoid means how we can define means, for example, if an hollow cylinder or hollow pipe will be present means on that one an insulating wire will be wounded. That system only we are calling as what's the thing here, solenoid we may call that. So in that insulating wire, when a current having I ampere is flowing means that solenoid is behaves as a bar magnet. Means when a current flowing through a insulating wire wounded on surface of any hollow cylinder, okay, in that condition what the thing will be happen, that the entire system will be behaves as a bar magnet. So for that thing compulsory one magnetic moment also present. So how we are representing that magnetic moment means, magnetic moment of solenoid is we are represented as capital M. Capital M is equal to NIA, means N is nothing but number of turns, I is nothing but strength of the current, and A is we are calling as area of the solenoid. Like that we will represent. See students, here one statement we are giving here: if many turns of an isolated wire are wound around a cylinder, the resulting coil is called a solenoid. Okay, this is the general statement we have. So this is one cylinder, you can think it, students. Here on this cylinder continuously we are wounded one insulating wire. Let in this condition capital N number of turns is present, I am thinking. So if you are passing a current through this wire means this entire arrangement will be behaves as one bar magnet compulsory. In that one here north pole and south poles are induced. Which one is induced? North pole and south poles are induced. So here I am mentioning here one more thing: when a current I passes through the insulated wire in a solenoid, that system is behaves as a bar magnet. So magnetic moment of solenoid is represented as capital M. Capital M is equal to NIA is the one fundamental formula. So where N is total number of turns in a solenoid we will prefer, and I is we are taken as the strength of the current, okay, and A is we are taken as here area of the solenoid. What is the thing, students? Area of the solenoid is the thing. Okay, students. One more concept once observe, students: magnetic field at an axial point of a current carrying circular loop. Magnetic field at an axial point of a current carrying circular loop we want to discuss. Actually this concept in okay, moving charges and magnetism, okay, in that concept we will discuss. Actually this is in next coming classes we will discuss, but once just recall one formula in this situation. Based on this formula only next concept we are able to explain. So once observe thinking, this is one circular coil I am given for you. Okay, students, this circular coil having how much radius is present? Capital R radius we are represented here. This is actually circular coil. That circular coil radius is we are taken as a capital R. So this is the center of the circular coil, you may imagine. So from center here at a point P, okay, we are maintaining some distance x. So at this point P we want to identify that magnetic field induction or magnetic induction at P we want to find out. So here students, here by derivations, by proofs, here we are getting B value is equal to mu naught Ni R square whole divided by 2 into R square plus X square whole power 3 by 2. This is one fundamental formula I am giving for you. B value is equal to mu naught Ni R square divided by 2 into R square plus X square whole power 3 by 2. Like this we can represent one formula. Here students listen carefully. Here small n is we are taken as here number of turns in the coil we are representing. If n turns present present in a coil means like this we are represented. Here small n is nothing but number of turns present in the circular coil. Okay students, next one more concept now we will discuss. See, as a question I am mentioning here, prove that a bar magnet and a solenoid produce similar fields. What is the question, students? See here, prove that a bar magnet and a solenoid produce similar fields. So just now we are already discussed about solenoid. In solenoid here on a hollow cylinder is present like that. Okay, on that one actually here number of turns is present. Let I am taking here total number of turns in this solenoid is I am taken as capital N. What is the thing, students? Total number of turns I am taken as a capital N I am taking. So students listen here, I am imagine here length of this solenoid is 2L. So here this is a midpoint O is we are chosen. So this is L distance and this is L length is present. So let imagine here this is coming from minus L to plus L. So totally this length of this solenoid is we are taken as 2L only. So and one more thing, students, here radius of this solenoid I am represented as a small a. What is the radius value for this solenoid? Small a is the radius of this solenoid I am imagining. See students, this is the midpoint. Okay, this is one axis. So this line is passing along that axis. So on this line here we are choosing one point P. Okay students, on this axis we are taken one point P. So that point P to center of the solenoid we are maintain distance R. Okay, from center of the solenoid to that point how much distance is there? Small r distance is present. So students listen carefully. Here I am choosing one small element having length dx, the two maintaining from x distance from the center of the solenoid. So this is x distance. Okay, x distance after, so we are taking here small element, that small element length is dx I am taken in that one, or in that unit length small n number of turns I am imagine. Small n number of turns present in a unit length I am taken. From diagram you may observe this is also we are taking as r minus x, students. Is it clear? Totally length of the solenoid is 2L, total number of the turns is capital N, small n turns is present in unit length, and center of the solenoid to point P distance is small r. Like that some assumptions we are taken. So those assumptions first I am taking here. Observe carefully. Let solenoid contains n turns per unit length. Let its length be 2L and radius small a. We can calculate the axial field at a point P maintains a distance small r from the center of the solenoid. This thing already clearly we are explained. Consider a circular element dx at a distance x from the center. This one also we are preferred. Okay, it contains n dx turns. Let I be the current in the solenoid. Means here in that solenoid current flowing is how much that current strength is I is we are represented. We know students just here in circular coils is also present in solenoid. So we know the magnetic induction at P is here dB is equal to I am representing mu naught n dx Ia square divided by 2 into here r minus x whole square plus a square whole power 3 by 2. This is from actually we know for a circular loop B is equal to mu naught ni r square divided by x square plus r square whole power 3 by 2. So with the help of this formula we can able to write this one. Is it clear, students? This is dB means a small amount of B value we can find. For getting total field here just we can do integration on both sides. So here integration applying means limits also we can imagine. Here limits is we are taken as from minus L to plus L. So here limits is we are preferred from minus L to plus L we can prefer it, students. So here total magnetic field here along the obtaining on integrating means in between x is equal to minus L to x is equal to plus L. So integral dB is equal to, here we are applying integration. Okay, mu naught n dx Ia square divided by 2 into r minus x whole square plus a square whole power 3 by 2. So students observe carefully. Here mu naught is constant, n is constant, I is constant, a square is constant, divided by 2 is also constant. Remaining thing what we will get here, integral minus L2 plus L dx divided by r minus x whole square plus a square whole power 3 by 2. This notation we will observe, students. Integral dv value is b only. So here I am just imagine, students, r minus x whole square plus a square whole power 3 by 2 entire value I am taken as r cube only. Okay, r minus x whole square plus a square whole power 3 by 2 I am imagine as r cube only. When it will becomes okay r cube means just we will refer here. See, students, if r is greater than a and r is greater than L, then only r minus x whole square plus a square whole power 3 by 2 is approximately we are taken as a r cube. So this r cube is also constant, we are represented outwards. So mu naught n I a square divided by 2 r cube integral dx minus L2 plus L. So on integral dx values becomes here x, we are getting limits minus L2 plus L. So then in next step here applied limits means plus L minus of minus L, this is totally 2L. So finally b value is equal to, we are getting like this, b is equal to mu naught n I a square into 2L divided by 2r cube. First we are finding this type of notation, students. B value is equal to mu naught n I a square into 2L divided by 2r cube we are finding. So for getting our result here I am doing multiplication and division with 2 pi. Multiplying and dividing with 2 pi. So b values becomes how much? In numerator just we are applying here 2 pi. Okay, means mu naught n I a square 2L into 2 pi. In denominator also we are applying 2 pi. Here 2 into 2 pi r cube. Denominator totally 4 pi r cube, there is no change. So in numerator slightly we will change here n into 2L I into 2 into pi a square. Like this we are arranging, students. N into 2L is nothing but total number of terms. Here a is nothing but pi a square. So we are getting here b value is equal to mu naught by 4 pi n I into 2a. So further I am writing, students, this is a 2 into NIA. So mu naught by 4 pi into 2 into NIA will divided by R cube we will represent. Okay, clearly we are mentioned a number of times here. Magnetic moment capital M value is equal to, in case of solenoid, NIA in solenoid. Is it clear, students? Therefore, instead of NIA, I can able to write b value is equal to mu naught by 4 pi into 2m divided by r cube. This is behaves as, okay, this is a relation appears as magnetic induction at a point P on the axial line of a bar magnet. Is it clear or not? This appears as a magnetic induction at a point P on the axial line of a bar magnet. So this is also the magnetic field of a bar magnet on axial line. There is a bar magnet and a solenoid produce similar magnetic fields. So bar magnet and a current carrying solenoid produces a similar magnetic fields. So finally we may conclude current carrying solenoid is behaves as a bar magnet only. Is it clear, students? Okay, students, next this is very important thing for you. What is the condition here? New concept means a small magnetic needle is set into oscillations in a magnetic field B. Obtain expression for the time period of oscillation. Means we want to find out time period of oscillating magnetic needle in a magnetic field. Okay, that thing we want to find. Actually for this one we will get a t is equal to 2 pi into I divided by under root I divided by mbh. Like that we will get it. So how we can find that one? Once observe carefully. Imagine this is one magnetic needle. So in this magnetic needle north pole is present, south pole is present. This is present in uniform magnetic field. Okay, maybe this needle makes an angle theta with that field. Is it clear, students? So that one is continuously oscillating once you can imagine. See, students, I am informing one thing. In your different materials, magnetic moment may be represented with small m. But for in my way I am taking this magnetic moment here capital M only. So for this magnetic needle magnetic moment I am imagine as capital M. Okay, see, consider a small compass magnetic needle of non-magnetic moment capital M of magnetic. Okay, and that one magnetic moment completed means then we are going for moment of inertia. For that one moment of inertia I am taken as I. Okay, is present oscillating in a magnetic field like this. We are represented. So if it is oscillating means students what will happen, a compulsory torque we are observing. Torque observing means okay, restoring torque is also observing. Restoring torque is nothing but the torque which is opposing the, okay, in opposite direction, the torque in magnetic field only. So here torque and restoring torques are in opposite directions. So restoring torque values were taken in negative signs. Okay, restoring torque compulsory we are taken in negative signs only, we can take it. So here students clearly observe, we know when a magnetic bar is present in a uniform magnetic field means torque value or couple value we people know tau is equal to mb sin theta. So here I am representing torque acting on the needle, tau is equal to mb sin theta. Here tau is restoring torque and theta is the angle between m and b. Restoring torque is in opposite direction. So here okay, tau value is equal to minus mb sin theta. I am represented. What I am represented, students? Minus mb sin theta I am represented. Here this is a restoring torque we are taken. So where negative sign represents opposition only. If theta is very small, sin theta is approximately I am taken as theta. So therefore tau value is equal to minus mb theta we are getting. So if theta is very small, sin theta value is approximately we are taken as theta, then tau value is equal to minus mb theta I am represented. This is I am taken as equation 1. So one thing students, in previously in rotatory motion and in system of particles chapter, one relation we are clearly explained, that is the relation between moment of inertia and torque. What is the relation between moment of inertia and torque? Actually we know that is one fundamental formula, tau is equal to I alpha, where alpha is nothing but angular acceleration. Okay, alpha is nothing but what? Angular acceleration. So angular acceleration, how we can represent? That is, we are represented alpha value is equal to d square theta divided by dt square. Alpha is equal to, what is the formula? D square theta divided by dt square. So tau value is equal to I into, I am represented here, d square theta divided by dt square. Let I am taking this is equation 2. So students, this is restoring torque and this one is torque. So both are tau values only. Just I am ready to going for equating both the things. On equating, students, just tau is equal to tau I am represented, I into d square theta by dt square is equal to minus mb theta I am represented. So this one is oscillating in magnetic field. Oscillating means just we can recall simple harmonic motion. In simple harmonic motion, acceleration is equal to, we know a is equal to minus omega square x. This is in linear conditions. But in angular conditions, this is angular acceleration, alpha is equal to d square by dt square, d square theta divided by dt square is equal to minus omega square theta only. Is it clear, students? So instead of d square theta by dt square, I am representing minus omega square theta, okay, is equal to minus mb theta. So both sides theta we will cancel, both sides minus will be cancelled. So finally we will get I omega square is equal to mb. So we know one thing, students, omega value is equal to 100% 2 pi by t. One relation we know. We want to find out which one that a time period only. So now I am writing here I into 2 pi by t whole square is equal to mb. So on simplification, I into 2 pi whole square divided by mb is equal to t square. T square is equal to root over 2 pi whole square I divided by mb. So t value is equal to 2 pi into root over I divided by mb. So this is the time period of oscillating magnetic needle in a uniform magnetic field. That value is t is equal to 2 pi into root over I divided by mb. These are the things. Okay, only two concepts were discussed. One is about solenoid and another one is oscillating magnetic needle in a uniform magnetic field. Okay, students, thank you. Next class remaining topics we will discuss it. Okay, thank you.